Okay, and this is number 9 in section 4.4. And see these problems in Algebra 2 and in pre-calculus all the time. So this is the best fencing plan. A rectangular plot of farmland will be bounded on one side by a river and the other 3 sides by a single strand electric fence. With 800 meters of wire at your disposal, what's the largest area you can enclose? And what are its dimensions? So we're looking to maximize the area. So I just call this width, and length, and this is a funny perimeter because we don't have this side because that's going to be the river. So we only need to fence these 3 sides. So my perimeter in this case would be just 1L plus 2W, and that equals 800. And this works out a lot easier if we just solve for L. We have 800 minus 2W. If we solve for 2W, we'd have a fraction. So this is a little bit easier way to go at it. Now the area, that's what we want to maximize, is equal to length times width. So this has got 2 variables. We need to reduce this to 1 variable, and that's this perimeter constraint is what we're going to do. This kind of locks it in. So now we have a relationship between L and W that's locked. So instead of writing L, I can write 800 minus 2W, and that's going to give me my area as a function of W. All right, I could do it as a function of L, but it would be a little bit more challenging as far as the arithmetic is concerned, or the algebra. Okay, so there's my area as a function of W, and then I can just multiply this out, 800W minus 2W squared, and that's fine. And we want to maximize that, so we're going to take the derivative, find the relative maximum. Now remember, W's got to be greater than 0, it's a dimension. Okay, and probably it's going to be, it's got to be definitely less than 800. You could figure out the domain if you want, but I don't think that's going to be a major issue at this time. Okay, so we take the derivative, and that's going to be 800 minus 4W. And it's not going to be undefined because it's just a straight line, so where is it equal to 0? We just set that equal to 0 to find the critical values or possible maximum. And we get, if I add 4W to both sides and flip it, I get 4W equals 800, so W equals 200. So there we go. So here's my function. And I can put my 200 here, and I can try values. I can try 100 and 300 into this. If I put 100, 800 minus 400 is positive. If I put 300, 800 minus 1200 is negative. That was easy to substitute in. So I'm positive, negative. So I'm increasing, decreasing. So it looks like I have a relative maximum at W equals 200. So that's my width. My width is 200. What's my length? Well, my length is, if I look all the way up here, remember the length is 800 minus 2W. So 800 minus 2 times W, which was 200, so that's 800 minus 400 is 400, so that's my length. So I've got my dimensions, and this probably would have been easier just to do it like this. I just found this could be a check if you want, but my dimensions are 200 by 400, so my area would have to be 200 times 400. 2 times 4 is 8, and I've got 4 zeros. 1, 2, 3, 4. So that would be the easiest way to do it. I also put the 200 actually in the area. I put the 200 in the area, and that was probably extra work. So area equals 800W minus 2W squared, so I put that in. I don't think you have to do that if you figure out the length times the width. It's a little bit easier. But if I put that in here, that'd be 800 times W minus 2 times W squared, and that worked out to be 160,000 minus 80,000, which was 80,000. This is another way to do it, but it's probably a little bit easier just to multiply the 200 meters by the 400 meters and getting the 80,000 meters squared. Okay? So I hope that makes sense to you all.